Hello, everybody. Welcome to another edition of Physics 150 Discussions with your host, Selman. So this problem that we're working on right now is Chapter 10, Problem number 4. And what it's asking for is, given the configuration that we have here, find the direction and magnitude of the current that flows in the horizontal wire that runs between the lower left and lower right corners. You always have to be careful about problems like this because it seems like they're asking for something very simple, just one little thing, the wire there, but it's problems like this that can often be very difficult because they're not leading you with multiple parts. They're letting you build the structure of the problem all by yourself. So we're going to have to work through a lot of that. And in fact, this problem is a little bit long. So what we're going to have to do is break this video into two parts. A previous iteration that I had done was running, above the 20-minute threshold. We want to cut most of these videos below 20 minutes because it seems like YouTube has got an issue with videos above that. So we're going to try and cut this into two sections that are hopefully balanced in the right way. So I'm going to go to a certain part. Maybe I'm going to set up all of the equations in the first part of the video, and then the second part I'll go through the algebra dealing with solving those equations. I think that that's a natural way to separate the two parts of the problem. Okay, so let's get started. So if we want to find the direction and magnitude of the current in that bottom wire, what we're going to want to do essentially is we're going to want to use Kirchhoff's rules because that's the way in which we really can extract some juice, like what the currents are given what we have. So let's write down what those rules are. So the first rule is that the sum of the potential drops across through a loop, those are equal to 0. And the second is that the current that goes into a junction has to be equal to the current that leaves the junction. This is conservation of charge, essentially. It's a conservation of the fact that there's some electrons going into this junction and then they have to also leave, okay? Very good. So we want to apply these rules. In order to do that, let's sort of just make some additional labels. What do we have here? We have to assign some direction to the currents. So looking at the left triangle here with the battery E and the resistor R, let's give the current that connects this segment right here. We got some, let's call this I1. Similarly, the current that runs from the second battery to the resistor that's 2R, let's call this I2. Now let's call I3 the current going through the resistor R3. That seems reasonable. And then I4 is going to be the current running through the resistor 4R. And then the bottom wire, this is the current that we want to solve for, the magnitude and direction. Let's call this I5. So we want to solve for I5. And also, let's also note that we have 3 loops here. I will actually write these out. So this is the left loop, this is the right loop, this is the center loop. And then we also have, so that gives us 3 equations for 3 unknowns. And then we also need 2 more because there's 5 total currents that we don't know, so we need 5 equations. Let's do this junction and the bottom left junction. So let me explain why I'm doing it like that. The 3 loops that I used, now in principle, there are many different combinations here. You could go with the entire outer rim is actually a loop as well. So you could do that, or you could connect 2 of those triangles to make 1 loop. there's many different ways that you could do this. You just have to remember that they're not all independent. So make sure that when you're choosing certain loops that you're not being redundant in your choice. And sometimes it's obvious that you're doing that, and sometimes what's going to happen is you choose a loop that's one too many, and what you get is something like 1 equals 1 or 0 equals 0. Basically, that additional equation doesn't give you any new information. Okay, so that's what would happen. It's just more work for you is what ends up happening there. So okay, let's back up on that. So let's get started, and let's actually start writing down these equations. So let's start with the left triangle. So let's do the loops first. And we're going to call equation so the left one is going to be the first equation. And let's go back up to look at what that loop looks like. So again, when you do these, you start, you can pick a place to start, and we're going to say that the actual current is going in the clockwise direction. Or we're just going to go around the loop in the clockwise direction, and we're going to add or subtract potential depending on how it comes about in the way that we've labeled these things. So if we start from the battery, that's going to be positive. You drop minus I1R as you go across the first resistor. And then you drop again, given the way that we labeled I4, you drop again with I4 times 4R. So let's write that down. So this is going to be minus I1R minus 4I4 times R, and this whole thing is equal to 0. So that's one equation. And we're going to have another equation. This is going, let's do this, the right triangle. So right number 2. This is the second equation. Let's look at what that one is. Now with this one, let's go counterclockwise. You're going to say, what is this ad hoc manner that I'm going around? It doesn't end up mattering so much with these loops, which way you go around. I'm just picking those directions because those are just going to give me equations that I'm more comfortable with. If I start with the battery being a positive number, for whatever reason, I prefer that. But if you go around the other way, it's just going to give everything a negative sign. So when you set that whole thing where every term is negative of what it would have been, then setting that equal to 0 basically doesn't matter. You can multiply that whole thing by -1. I don't want to get too into the weeds. You can try for yourself and see that indeed it gives you the same answer. So here, we're going to start from the battery, 2E, and going around counterclockwise, you're going to get a potential drop at the 2R resistor and another potential drop at the 3R resistor, okay? So we're going to have 2E minus 2I2R minus 3I3R, and this is all equal to 0. There's also the center equation, which is number 3. And this one, let's go around this one counterclockwise as well, so that the current going through, there's a positive let's see if if it doesn't end up mattering, but what you want to do is pick one of them to be positive And then if you go around in any particular direction, you're going to see that the other one is negative. So what that ends up translating to is that you've got 4I4 times R minus 3I3 times R equals 0. Had we gone the other way, that would have been a relative minus sign between them the other way, negative 4 plus 3, but that's still the same equation essentially. So now let's look at the junction equations. So at the top one, what you see is that I1 and I2 are coming into that junction, I3 and I4 are leaving it, so that leaves us with a junction equation this is equation 4, and this is going to be I1 plus I2, that's the current going into the junction, is equal to the current leaving it, which is I3 plus I4. And there's going to be another junction equation, equation 5. Just looking quickly back at what that one looks like, what you see is that I4 is coming into it. So we're back here. And so you've got I4 coming in, and then I5 leaving it, and I1 also leaving it like this. So when we write that out as an equation, you see that this is I4 equals I1 plus I5. And now, okay, so what I'm going to do here is I want to note that what we want at the end of the day is I5. So part of the reason that I wanted to pick this junction is because it directly introduced I5 into what we were doing, and that's exactly the one that we want to solve for. So let's sort of lay out a strategy for how we're going to solve this problem. Essentially what we've done is all the physics. Now we're just going to be doing the mathematics, the tedious algebra involved in actually solving these equations. We've got 5 equations for 5 unknowns, I1, I2, I3, I4, and I5. So the strategy that I'm going to pursue here is I'm going to use equations 3, 4, and 5 to obtain these currents, I3, I4, and I5, in terms of I1 and I2. So I'm going to use the latter 3 equations because if you just take a look at them, they clearly relate most of the currents to each other. Now we want I5 at the end of the day. So equation 3 relates I3 to I4, and then equation 4 relates I3 and I4 to I1 and I2. So my strategy is just going to be, okay, if I want I5, which is related in equation 5 to I1 and I4, I'm just going to try and write I5 in terms of 2 variables. Essentially, I can choose which variables those are. I'm going to make a choice to make those 2 variables I1 and I2. And in equations 1 and 2, I'm going to solve for I1 and I2. So the strategy is to use those 3 equations to find I3, I4, and I5 in terms of I1 and I2. Then solve for I1, I2 using equations 1, 2. Okay, that's the basic gist of what we're doing. So let's actually get to what I'm gonna do right now is I want to make sure that we have enough time on this. One moment. So what I'm going to do is pause the video right now. We're going to take a break, and in the next video I'm going to go ahead and solve all of these equations algebraically. Okay? So I'll see you guys in the next video.